Hello and welcome to my video series on contour integrals. In this video we're going to look at what a contour integral actually is and how we can go about computing them. So to start off with, if we think about integrating over the real axis, so we have x is a real number, are the real numbers, this is our f of x, and we're going from some point A to some point B. Got a function that looks something like this. Our integral is just the area under this function, and that's reasonably straightforward to see what that means, and we can go about calculating that in familiar ways. If, however, we're trying to integrate between 2 points in the complex plane, so this will be our real axis, so our imaginary axis, say we've got 2 points in the complex plane that we want to integrate between, there are a few more questions that come up. So how do we actually get from one point to another? Is it a simple straight line-ish? Are we looking at a more triangular shaped line, curve between them? Or are we doing some great big loop to take us from one point to another? And so this is going to determine how we go about integrating between these points. So what we actually need is, if we have real numbers a and b, what we want is a function that's going to describe our curve. So let's say our gamma that goes between our a and b to the complex plane. And so using this gamma, we can go about doing the integral. And we'll say we call this curve capital gamma. So this is going to give us a name for the path it takes. So what are the restrictions on gamma? So gamma has to be piecewise continuously differentiable. And this is what's going to allow us to do the integration. So what does this mean? This means that in each of the chunks of gamma, you can differentiate as many times as you want. Basically means you can have as many corners as you like, as long as it's a finite number. So you can't have an infinite number of pieces, but you can have a finite number of different sections of your curve that are all continuously differentiable. So what would an integral look like? So say we have a function that goes from our curve to the complex plane. So what this means is a function takes values along our curve and gives us back complex numbers. And we want to integrate over our curve. We'll do f of z dz, where z are the complex numbers that lie on this curve. So what we can say is that z is gamma of t for some t, and we can use this as a substitution. So where dz by dt, just gamma dash of t. And so we can see that using a substitution, our integral is just the integral from a to b of f of gamma of t gamma dash t dt. And so this has simplified the problem somewhat, because now we're doing an integral over real valued variables. The issue we have now is that f gives us back complex numbers. So if we were to have a different function, say u, which goes from the complex numbers to the complex numbers, and we take a real integral over u of t. So this is going to be a bit simpler for the notation. So we've got a real integral, a real valued variable, but this gives us complex values. We know that we can split this in each case to the real part of u of t plus I times by the imaginary part of u of t, which is what you can do with any complex number. And now, using our normal rules for integration, we'll have this as the integral from a to b of the real part of u of t plus the imaginary, I times by the integral of the imaginary part of u of t dt. And so there we go. So using the combination of this and this formula, we can take a complex integral and break it down into the sums of a real integral plus I times by another real integral. And so maybe we can apply an example now. So let's say we want to integrate over a circle in the complex plane. So we center it at z0. It's got some radius r. This is our real. This is our imaginary. And we want to know what the integral of this around this circle is. And let's say our f, so we'll call this gamma, f, which goes from gamma to the complex plane, where f of w equals 1 over w minus z0. And this is going to be an important example for the future, so it's going to be really good to do this now and to have a good idea of how it comes about. So we need to think of a function that's going to take us around this circle. So the most basic one just goes from 0 to 2 pi, where gamma of t equals r times by e to the it plus z0. So you can see, using this, how we get to this circle. So at 0, t equals 0, we're here, and we just go all the way around. And it's important to note that the positive direction is always counterclockwise. So just like when you do angles, always go around counterclockwise for positive. If you went around the other way, it would be negative. So what is our integral? So integrate over gamma f of z dz, and we know that this is equal to the integral from 0 to 2 pi of f of gamma of t, gamma dash t dt. So 0 being our a, 2 pi being our b, these are the limits of the integral when we look at t as a real number, a real valued variable. So going about integrating this, we've got 0 to 2 pi, f of gamma of t is just this value here, minus z0, 1 over that, which is just 1 over r e to the it, and gamma dash of t we can see is just I r e to the it. dt. And so this part cancels with this part, and we end up with integral from 0 to 2 pi of just I dt, which gives us 2I pi. And what's worth noting is that this is irrespective of the radius of the circle. So when we look back at our original diagram, it turns out that r didn't matter. We could have had a huge circle, a tiny circle, and we've got the same integral as 2I pi for this function f. In the next video, we'll look at the ML inequality and some of the consequences that has.